Hello students, welcome to HD Labs. What we are going to discuss today? We are going to discuss today a micro topic. So first of all, let's talk about the main topic. The main topic is once again the mechanical properties of solids. But in this, I'm going to discuss with you a micro topic, a small topic, but I'm going to discuss that holistically. The topic is the mechanical strain. So let's kickstart this particular session to discuss about mechanical strain. Great. So what is strain? Strain is supposed to be something we like to measure. And once an object at a material is subjected to stress, then we are allowed to do so. You heard me correctly. That when I'm going to talk about a strain, I should always be understanding that first of all, that particular material must be subjected to stress. Without stress, there is no measurement of the strain. What I'm going to hence talk to you about in this session is about the varieties of that particular strain. So, strain is nothing but a relative measure of the change which has been produced in a material whenever that particular object was subjected to strain. So that's a relative change in the dimensions, size can also be stated, or the shape of a material when it is subjected to stress. So don't forget that particular part, right? Subjected to stress. If the object is not subjected to stress, there is no measurement of the strain. Now, when I'm talking about a strain, I can classify this into three hierarchies, three parts. The first one is linear strain. The second is known as volumetric strain. And the third is known as shear or tangential strain. So let's now understand about each one of them in detail. So first of all, let's focus upon what is a linear strain. Now, the linear strain is further split into two kind of the strain. The first one which I'm going to discuss with you is a longitudinal strain. Now, what is a longitudinal strain? The linear strain is known as a 1D strain. That means the changes which we are watching is supposed to be in one dimension only. So to understand that, let's take an example. An example for this is, suppose we have a wire which is suspended from a support. And what do? We apply a hook, and with the help of a hook, we are actually placing the slotted weights. And as we keep on adding on the weights, we are adding to the stress subjected to the material. So there is a stress, as I said, before checking the strain, you must focus on the stress. So there is a stress which is there because of the applied load. Now, because of which what happens, we are able to see, we are able to observe, we are able to take a reading that the length of this material undergoes a change. So if L was the original length of the material, now there is an extension produced in this which is delta L, and while you are checking that extension, you can have a scale placed next to it to measure that particular extension. That extension is in the direction of the load which is applied. First of all, when I'm writing the longitudinal strain, there's a change in the length upon the original length. So it is talking about a change in the dimension of the object and not about a change in the shape of the object. And this is clearly a 1D strain. And when I'm talking about the units of the strain, it isn't there. Reason, because the numerator and denominator are measured in the same units. So the units aren't there. So this is a term which doesn't have any unit or any dimensions. So delta L upon L is a 1D strain, and as I explained, this is measured in the direction of the load applied. Now, the longitudinal strain is a linear strain, and there is another kind of linear strain which is known as a lateral strain. And what is a lateral strain? As you can see in the animation, when you're applying the load, you can see that the diameter of that particular material is subjected to a change. So let's say this was a material and which was applied with the normal stress is like this. Now, as a result of which, what happened? That this particular material got stretched, and as it got stretched, so what happened? The diameter of this was decreased. Of course, the length increased. So I'm not focusing on the length right now. I'm focusing that there is a decrease in the diameter. Where was a load applied? The load was applied in the linear x direction, let's say, and the diametrical changes are supposed to be observed in the perpendicular direction to it. So if I'm checking the diameter over here, that let's say this was supposed to be d, and now I can see that there has been a decrease in that particular diameter. So now that's the new diameter which is coming out to be lesser than the original diameter. If I sketch that particular figure inside the first one, so we'll be able to see it better that this exactly what happened. And so there is supposed to be the changes which are produced over there, but these changes are perpendicular to the load. So delta D upon D is defined as a lateral strain. You can also write this equal to delta R upon R. Reason the diameter is equal to twice of the radius anyway. But being a 1D strain also is a different from the longitudinal strain because it is occurring in a direction perpendicular to the load applied. So these are the two kinds of the strain. Let's move to the second variety of the strain, which is known as a volumetric strain. And this is, of course, arising because of the volumetric stress applied. So you can see that we have a cubical structure here and which has been applied with the pressure on all the sides or a uniform stress on all the sides, because of which from every direction the size of it decreased. So we can easily say that the volume of this has gone a change. So we are going to check the initial volume and the final volume and check the difference in the volume. We define this as the change in the volume measured relative to the original volume is known as a measure of the volumetric strain. Simple. It can be positive, it can be negative, meaning the positive is that suppose we decrease the pressure, this object may grow in size and therefore the delta V becomes positive, the final minus initial volume. So the volumetric strain is going to be positive. And if suppose because of an incremented pressure, the size of this got decreased, so there is a decrease in the volume, so we are telling that the volumetric strain is going to be negative. But do remember that even if we are talking about a 3D strain, volumetric strain is kind of a 3D strain, but we have got no change in shape. So the linear strain also and the volumetric strain both are because of the normal stresses, and hence they are measuring a relative change in the size or the dimensions. So who is going to talk about the shape changes? So for this we are talking about a shear strain. Now let's understand the shear action. So this is the object and we apply the force on this object by selecting a particular layer. So I selected the topmost layer of it and I'm applying the force on the topmost layer tangentially. So I am subjecting this layer to shear stress. Now the lower layer is relatively not moving, reason because the force is applied only on the uppermost layer. So there is a change in the shape because of the torque which is applied about this particular point by the action of this force. So this vertical line over here, let's say that is OA, gets rotated. The entire structure actually gets rotated. This particular point reaches here, and so this entire structure gets a change in shape. Let's identify the shape. So we can say a cuboidal structure has been converted into a parallelopipe. Now that has to be measured by some amount. So what is the measurement here? That's quite simple. That is line OA, which was initially perpendicular to the fixed surface, has been rotated by some amount, and this has become the line OA prime. So the amount of rotation which has been produced can be measured via an angle. Let's mention that angle as theta, and this theta as an angle is known as angle of shear. And my friends, this angle of the shear is what we are measuring as the shear strain. So, this theta can be measured by that small triangle, this triangle. Now see that this is a displacement of the point A. That's a linear displacement. That's understandable because the force is applied in the tangential direction. So that point A moves in the same direction. There's kind of a work which is getting performed in the same direction. And let's say it travels a distance of x. It shifts a distance x, linear distance. And let's say this is labeled as h. So I can use theta over there as equal to x upon h. Remember, I'm talking about a solid. So solids are mostly rigid. They are mostly rigid, right? So this theta value is going to be smaller. So the theta is written from there. If you write tan theta, that's going to be x upon h. But since we are talking about a smaller angle, so the tan theta can be written as theta, because imagine that you are having a steel cube or steel cuboid and you're applying the force on the topmost layer of it. Will you see the deformation of it? Oh, I don't feel so. You will not be able to see that particular angle with the naked eye. With the microscopic view, you might be able to see that particular small change in the angle. So the theta of those approximation can be written as equal to x upon h. So what is strain basically? The strain is a relative change in the dimensions or the shape. But specifically when I'm talking about a shear strain or the angle of the shear, I'm talking about a change in the shape. So this theta as an angle basically explains to me the amount of the change in the shape. If suppose the theta is 0, that means the shape remains the cuboidal. But if it is actually getting more, so it is getting deformed more in the shape. So that's the angle of the shear and also the shear strain. So it is pretty much clear that when I'm talking about a linear strain and I'm talking about a volumetric strain, so I'm going to talk about the change in the size or the dimensions. And when I'm going to talk about a shear strain or the angle of the shear, I'm going to talk about a change in the shape. So that's our mechanical strain types. So let's have an overview of it. So we discussed about the mechanical strain, which is of three varieties. First of all, of which is a linear strain, which is further divided into two categories as a longitudinal strain, for which we checked upon the expression as delta L upon L, and this was in the direction of the applied load. So it was measured in the direction of the applied load. And then we talked about the second kind of the linear strain. Do you remember linear strain is a 1D strain? So it was lateral strain. Lateral itself means transverse or perpendicular. And you measure this as delta D upon D or delta R upon R. And this was measured in a direction perpendicular to the applied load. The second variety of the strain which we discussed about was volumetric strain. And the volumetric strain is a 3D strain, and it is once again because of the normal stresses. So there is a point to be checked upon. When I'm talking about these, I'm talking about the normal stresses inducing them. Do also remember there is no strain measurement without the stress. So the normal stress was applied, and because of which we are getting the strain, which two kinds, linear and volumetric. Volumetric is of course because of the uniform stress, or we can say the pressure variations. Great. And the final kind of the strain which we talk about is known as a shear strain. And the shear strain is typical reason because it causes a change in the shape. So that's a relative change in shape. While when we are talking about the linear and the volumetric strain, we are talking about the relative change in dimensions. So we are pretty much clear with the article of the strain now. Do remember that the strain is a dimensionless quantity and it doesn't carry any units. And the strain is always under the influence of the stress. To finalize this article, complete the article, Let's take a small example where we have a metal rod, and this particular metal rod is having a length of L, and this was at a temperature of T naught, and this was heated. So it expanded, and it expanded to the new length that was supposed to be L prime. And you can physically see that L prime is more than L, and you can actually see that there has been some extension. But could you please answer that what is the amount of the strain in this? So an obvious kind of a answer can come out to be, sir, that's a delta L upon L. That's the difference in the length upon the original length. But the answer for this question is not what it's looking like. The answer for this particular question is that the longitudinal strain in this rod is zero. Why it is zero? Because it's a free expansion and this rod isn't subjected to any stress. This is freely expanding and therefore the longitudinal strain is zero. So my friends, do check that particular point, that whenever you are measuring the strain, just check before that whether the object was subjected to the stress. So that's all for the today's session. I hope you enjoyed every bit of this particular session. Thanks for watching. Bye.